Okay. Okay, well, welcome to the class Advanced Finite Element Methods. As I already introduced myself, my name is Alejandro Aragon and I work at Precision and Microsystems Engineering. I teach this class together with another more advanced class than this one that is called Enriched Finite Element Methods, for which this class is a prerequisite, by the way. And I always start with this image. Actually, this is art. This has nothing to do with finite elements, but I really like this image because it basically encapsulates everything that we're going to be doing in this course. Right? So what you see here is a high resolution coming from optics. This is an artist from Spain. And what you see is basically different levels of resolution of the same object. Right? And this is exactly what we're going to do in this course when we talk about finite elements. So we're going to try to analyze an object, very complex object. And then what we try to obtain is an approximate solution to a boundary value problem. And of course, what we do is we try different levels of refinement because we would expect that as we refine the finite element mesh, that is, as the finite elements get increasingly smaller, that our solution would be better. That it's intuitive, right? Okay, but let me tell you a little bit about the outline for the course. So we're going to start with an overview of the standard finite element method. So we talk about the strong form of the problem. It's basically your differential equation and your boundary conditions are together called the strong form of the boundary value problem. Because it is very hard to solve the strong form of the problem, normally what we do is we try to find an approximation. So we pose the problem in what we call a weak form or variational form, okay? And that is, of course, here the next step. Still, this weak form that basically satisfies our boundary conditions and our differential equation on average over our domain, right? It's still in an infinitely dimensional space, right? That basically means that I'm not going to get too mathematical in this course, but we're going to look at some mathematical concepts that are important for you to understand the literature. If you read a paper on finite elements, you understand what they are talking about. But the idea is that since we are in an infinitely dimensional space, the weak and the strong forms are equivalent. Okay? Now, we cannot solve an infinitely dimensional problem in a computer. We have a fixed amount of memory, and therefore we rely on a subspace of that infinite dimensional space, and then we do what is called the Galerkin projection. And this is basically how we come up with our finite element equations. We're going to talk about some important properties about this Galerkin projection, right? We're going to talk about the orthogonality of the error. We're going to find out that the finite element solution is actually the best solution that we can get in that finite element space. We're going to talk about spaces. And then, well, we all do this in an isoparametric setting. We're going to talk about what that means, superparametric, subparametric. The idea of isoparametric is basically that we approximate our geometry with the same shape functions as we approximate the field. So if we're solving for the displacement field, and that displacement field, let's say, is a quadratic polynomial interpolant, then if I approximate the geometry with a quadratic polynomial, that formulation in particular is called isoparametric, okay? So that's for now. And then all of this is happening in a 1D problem. That's why I'm saying that really you don't need a prerequisite for this course, right? Because we're starting from scratch, from the very beginning. So everything is going to be done in 1D so that you understand the concepts. And why is that? Well, because when we move to higher dimensions, most of these concepts remain the same. So we don't have to do something extra. There are some caveats here and there, but overall, the behavior in higher dimensions is the same. So we're going to talk about the strong, the weak, and the Galerkin forms also in higher dimensions. Now, so far, everything I'm talking about is what we call the H version of the finite element method. That basically means that you would expect that as you refine your mesh, that you get a more accurate solution, right? So we're H refinement. H is normally the symbol that we give to the mesh size, right? So if we have, let's say, a mesh with H equals 0.1, that basically means our intrinsic length of my finite elements is 0.1. 0.1 what? doesn't really matter, right? As long as we work with consistent unit systems, it could be meters, it could be kilometers, whatever we want, okay? And that's normally the way we work with finite element packages. So if you ever used Abacus or another package, you probably note that there are no dimensions. Well, that's because you have to work with consistent unit systems. But now there is a different type of finite element method. There is what we call the P version of the finite element method. So anyone has an idea what this means? P version of the finite element method? Okay, so in the H version of FEM, what we do is normally we assume that the finite elements have a linear or a quadratic at most polynomial interpolant, right? And therefore, in order to get better accuracy, you basically reduce the size of the elements. Okay. Now, in the P version of the finite element method, you can keep the size of the elements the same, and then just increase the polynomial interpolant. So you can go cubic, quartic, quintic, and so on, and therefore you obtain a more accuracy that way. So what we will find out is that for a lot of problems, the P version of the finite element method is more accurate, right, than the H version of the finite element method. So this is something that most people actually don't know, and it's a pity because you don't have that capability in lots of finite element software. So we will look at how we construct these P version interpolants, and what we are going to use is something called hierarchical polynomials. So basically we start with the same roof hat 10th functions that we were discussing a few minutes ago, and then we're going to keep adding quadratic, cubic, quartic, quintic polynomials on top of that to build a better interpolant for our solution. And then we will look at what, yes?
Are we always thinking about polynomials, or are we also going to talk about the Fourier transformation using sinusoids?
Yeah, the question is if we're going to always talk about polynomials or we're going to use other functions. So in this course, we're only looking at polynomial interpolants, but there are, of course, many things that can be done to obtain an approximation. Indeed, as you say, you can just rely on Fourier series, for instance, as basis functions, and that was actually something that predated the finite element method. So back in the day, if someone knows the Rayleigh-Ritz method, have you heard about the Rayleigh-Ritz? Okay, well, this method basically assumed this type of functions, trigonometric functions, but the problem with this is that the functions have global support, so they are basically spanning the entire domain, right? And therefore, the resulting matrix is basically a dense matrix that is harder to solve than if you have a sparse matrix, right? So we are not going to look at Rayleigh-Ritz type of approximations in this course. But what I'm going to say is that this course is actually a prerequisite for the next one, which is enriched FEM. And in enriched finite element methods, what we actually do is we can actually take any type of behavior that we know about the solution to a problem and incorporate that into the approximation by means of what we call enrichment functions, right? So for instance, if I know that I have a crack domain, and there is a crack, and then I know what is the asymptotic field close to the crack tip, there is a singularity there, I can actually enrich the approximation by means of these functions to improve the accuracy. In other words, in the next course, we're not going to be limited only to polynomial interpolants, okay? So one of the things that we are going to look carefully is at convergence, right? And this is the main point I want to teach you in this course, because when you go to the industry, I would like you to see the finite element package that you use and to understand what's happening and how to improve the solution, right? So you may wonder, well, if I don't have the exact solution to a problem, how do I know whether my solution is any good? And I can guarantee you that none of you know how to do that. Who knows how to do that? Those of you who have handled a package before. Yeah, and the reason is that people don't teach you these things, and this is, for me, the main thing that you can take from this course. So if you obtain a solution, how can we do to improve the accuracy, right? Maybe it's not very accurate here, maybe there is some singularity, maybe we need to refine locally the mesh, and this is a sort of thing that you can actually learn in this course. How do we obtain what we call an estimate of the exact strain energy, so that we can use that to do a convergence analysis, for instance. These are the things that you're going to learn, and I'm sure you're going to learn them, because if you finish the final project, then this is going to be there, okay? So we're going to look at a priori error estimates. So in essence, what we're going to do is to learn theoretically how the finite element method converges when you refine the mesh or when you increase the polynomial interpolation, right? And we're going to do something called a posteriori error estimates, which, as I said, you can actually estimate what is the value of the exact strain energy for your problem, even if you don't have an exact solution. And this is very powerful, because if you have an estimate of the exact strain energy, right, then you know what you have to do to improve on the solution, okay? And of course, computer implementation aspects are all over the place in this course. As I said earlier, you're going to be given a finite element code that is actually working in Python. So the first version of this course, that was not done. I was actually giving only pseudocode to students, and the students were asked to write a finite element package from scratch. And you can imagine that didn't go very well for me, right? So I actually had only 2 projects, the first edition of this course, and then I had to change something. So now you are given a finite element code that works. You run it immediately, everything works fine. It's not even, there are no tricks, right? It just works, hopefully. But then, of course, this is what you have to modify to solve the problems in the project, okay? All right, so course objectives. Derive the finite element discrete equations starting from the equilibrium equation or any other elliptic partial differential equation. So in this course, we're not going to look at more advanced partial differential equations, parabolic nor hyperbolic. We're going to focus on simple elliptic partial differential equations. Identify the limitations of finite element methods and understand the means to overcome them. Evaluate the performance of the method on academic problems. Extend the software package provided to simulate complex problems. So these are the objectives of the course. As I said earlier, also for me, the main objective, and that is the reason I started teaching this course, is that students go out from the university, and when they use a package, they really understand what's happening behind the scenes. That's for me was the main motivation. So the material is based on a book that we are going to call Fundamentals of Enriched Finite Element Methods. So I'm one of 3 authors. The other are Armando Duarte at the University of Illinois, and then Angelo Simone at the University of Padova. The book is in progress. So for those of you who have already received an invitation to join the course in Nota Bene, you have already perhaps seen the first chapter that we're going to look at. So please don't share this with anybody, because we have signed already a contract with Elsevier, and we have asked for a deadline extension for September this year. So the draft was supposed to be ready now in February, but yeah, well, we have other things to do, so we are trying to push the deadline to September. But it's happening. We have already about 180 pages in this book, and the course material is based on that. So please don't share that material with anybody, okay? Now, we keep the copyright, right, of the book. That was a tough negotiation, but that doesn't mean that we can just go around and give this to anybody. So we can actually share a little portion of the book. Okay, the Nota Bene is a system that we're going to use to interact. So we have a face-to-face session here every Tuesday, but we're also going to interact online. So this is an incredible system that allows you to basically read the content, the book, and then annotate. So if you have questions, you can just write the questions directly in the system, and you can interact with one another. So you can reply to someone's question, and if I see that there is really no interaction, then of course I jump in and then I give you some answers. This is a system I've been using all these years, and it actually works incredibly. So in order to access the chapters, you have to send me your username, because then I have to add you to the system, okay? So please do so. I already have a few emails with the username, and I've been able to add some of you, but of course not all of you are there. Yeah?
Do we have to keep emailing you to get access to the other chapters? Or?
No. Once you email me your username, you should access everything. So right now there is only the syllabus there and the chapter, this chapter, review of finite element method. Okay, yeah, these are some of the people who I managed to input in the system so far. And then, of course, we're also going to interact through Brightspace, so announcements are going to be posted there, so please check regularly if there is something going on. And I'm also thinking in uploading the videos from this class to Brightspace, so that you can access also the content that we see here online. Although I must say that I have all my courses on YouTube as well. So how many of you have seen my website? Okay, 3. Well, in my website, then you can get to the education, and then you can get access to all the videos on YouTube. So that is something else you can do if you want to revise material that we have seen here, either through Brightspace or through the YouTube videos. Okay, so there is one assessment, one final project, 100% of the grade, as I said, and I'm going to repeat it. I can give you a 10 for this course if everything is perfect. There is no reason for me not to give you the highest score. And if you did awfully, right? If you really didn't do well, and you get a very, very low grade, I'd rather tell you than to lower your GPA, because again, I'm not interested in getting everybody on certain date. I'm very flexible with the deadline, so you can actually bring or send me your final project anytime you want. What I'm interested in is that you learn the content of the course, okay? And that is a bit dangerous, right? Because then you say, oh, I can finish this any time I want. And as I said earlier, yeah, there was someone who gave me the project 2 years after, and he got the grade. But then in the meantime, I mean, you can imagine, okay? So I know you are doing lots of things, but really try to not to leave things behind, because it is advanced content, and to get back is going to be harder than just doing it right from the beginning. So that would be my advice. I will also provide you with a template, a LaTeX template for the final report. So I normally ask for a written report with at most 10 pages. So you also organize yourself, because sometimes students, before they were giving me a report with 80 pages, I'm like, okay, I cannot spend time for reading 80 pages of a report, right? Although now I have someone, a PhD student of mine, is actually helping me with the grading for this course as well. And prior knowledge, as we discussed, well, you need some knowledge about programming, and Python is a language that we will be using. In the past, only a couple of students suggested using MATLAB, and they managed to finish the project in MATLAB. But of course, I would strongly recommend that you learn the language. This is a great opportunity, so that at worst you can put Python in your CV as one of the skills that you learn at TU Delft. So that would be fantastic. Besides, it's a really, really great world. Python is amazing. So I really strongly recommend you that you learn, because it's just it's an incredible world. And talking about Python, tonight we have the first crash course, and only crash course, right? So I'm not going to be teaching Python, but I will give you some resources in case you need to sharpen your Python skills, okay? Okay, so as I said, this is, yeah?
Is the project individually, or
yeah,
a group of?
The project is individual. You really cannot do the project with someone else, because it's detrimental to your own. Yeah. So of course you can do it, but I mean, what's the point, right?
Yeah.
But I do have some tools to check whether you have done the project yourself, because I actually ask for everybody to send me their code. And yeah, I did have a problem in the past with a couple of students who were doing this together. And what happened in the end is that I actually had to take a final examination that was an oral examination, and I did realize that one of them was.
Yeah.
So of course, I mean, I trust people. I really try to see the best in people, and of course you can cheat on this course, right? But if you get caught, you are in trouble. Yeah. So why? Besides, you don't learn. I mean, and this is an elective course. It's not like a mandatory course that you don't like, right? So you guys are here because you really want to learn about finite elements. Anyways, this course is a prerequisite for enriched finite element methods, ME 46080. And I'm just going to give you a brief overview of the things that you would expect to see if you actually join the next course. Because, in fact, the other motivation I have is for me to basically teach what I love, and I love enriched finite element methods. That's actually what I do for research. So, well, there are many types of problems for which enriched finite element methods are actually better than standard or the H version of FEM. And here are some problems. So those who require complex remeshing, so very complex geometries, or those for which you have evolving geometries that would require remeshing, like crack propagation, coalescence, branching, merging, optimization, topology optimization, for which the geometry is actually not really defined, but it's actually the result of the optimization. Moving boundaries, like multi-phase problems, solidification, those type of problems. Immersed boundaries, you can use enriched FEM to basically just enclose or immerse whatever domain within a bigger mesh, and then obtain the solution as if you actually had meshed the immersed geometry. And then, well, more recently we have done some numerical or physical interfaces like contact. So we have proposed some new procedures for solving this type of very highly nonlinear problems. And then non-smooth problems with singularities. As I said, you can enrich your solution space with some asymptotic functions that have some sort of singularity towards a crack tip, for instance, to obtain better approximations. Problems with localized or sharp solution gradients, like, for example, applied heat fluxes that are very local. You can solve those with a single finite element, high gradients with a single finite element, which is something incredible. And well, if you need, for instance, to do many finite element analysis just by changing the geometry, internal geometry, well, you can make the use of these enriched finite element methods to basically get a plethora of results with a single finite element mesh, because the idea is that we can decouple the finite element discretization from the geometric features of your problem. That is basically what we do. And I'll give you some examples. So here, for instance, you have, on the left, you have a standard finite element mesh that you would require. On the right, the enriched FEM equivalent. And the results are actually very close. This is something that I got from my PhD work. Here, you have some examples of some woven composites that you can actually model. Everything is decoupled from the finite element discretization. So your finite element mesh is actually structured, very simple to create, but then anything else is basically immersed in that finite element mesh. Some problems on microstructures. Here you have a propagating crack. Then you have damage evolution in composites. Again, all those spherical particles are independent from the mesh. And here, for instance, what we're interested is in trying to see what is the damage pattern that is created by first applying an in-plane strain and then basically pulling in mode 1. So we're opening and then we are seeing where it should fracture, which is basically the red parts. And then, well, fracture propagation. So this is, thanks to Armando Duarte, this is a propagating crack due to the pressure of water in one of those hydraulic fracture. This is a hot topic in terms of oil extraction. So this is actually a very advanced simulation. Again, this crack is propagating completely decoupled from the finite element mesh that is used in the background. And then, well, we talk a little bit about this sharp gradient. So you see that if you want to capture this localized heat load, then you need to refine the mesh. Otherwise, you don't capture the sharp gradients. But if you can also enrich with a function that can do that, and then you see that with a very coarse finite element discretization, you manage to capture that, and that is because again we are enriching the approximation space by some functions that can actually reproduce this behavior. So the finite element or the Galerkin procedure is not confined to polynomial interpolants, but you can actually add anything you know about the solution of a problem to improve on the accuracy of your approximation. And yeah, this is also one of the examples from my group. So we basically have an immersed type of finite element method, and for this case we just immerse a beam and we obtained an eigenvalue, the first vibration mode, but we rotated the mesh just to show that we can actually completely immerse and then have a finite element solution that can live within another bigger finite element mesh. And the last thing I'm going to show you is this. This is our formulation applied to contact. So we are enriching the interface between these two solids, and then we are nicely able to transfer the contact tractions from one solid to the other. This is a very tough test called the ironing test. So our formulation is being used for that. Okay, so let me finish here. This is a quick presentation of what we're going to see in this course and what you would expect to see with if you finish this course and you take the next one, right? I will take any questions now.
Do I need to bring your laptop to the class?
No.
I'll just remember.
No need to bring your laptops to the class, unless of course you take notes. But if you take notes, I'd rather have you taking notes properly, because taking notes with typing doesn't make much sense. Yeah, you have a question there? So, what is the advantage of doing finite elements in Python with compared to MATLAB? Or C++. Okay. So now you're basically talking about what is the difference between Python and other programming languages, and why I chose Python. Because okay, finite elements you could indeed do in any programming language. Okay. So there are two types of programming languages. You have the interpreted languages like MATLAB, like Python, and then you have the compiled languages like Java, C++, C, Fortran. Now, of course, the difference, you should perhaps know them. So compiled languages are performing much faster, right, than interpreted languages. But of course, you have to compile code, right? And therefore, interpreted languages, the development process is faster. You don't need any compilation. But programming languages like C++ require a very steep learning curve. So in my experience, when I was doing my PhD in the US, I took one course where I learned to program in C++. And after 6 months of learning the language, I thought, okay, now I know C++. 1 year after I started learning C++, I thought I knew C++. And then I read a book that taught me that I didn't know anything about C++. Right? So Python doesn't have that problem. Python is a programming language that I mean, actually, if you read it, you understand it. Right? Learning the syntax is very straightforward, and you don't need a steep learning curve to learn. So I'm not going to compare, of course, Python with compiled languages, because it would take you only 6 months to learn a little bit about C++. Okay. Now, with respect to MATLAB, well, Python is free, right? So as soon as you leave the university and you know Python, well, at least you know a language that you have a skill set that you can apply immediately without having to buy a license. And that is basically the main motivation for me to use Python for this course. I have nothing against MATLAB. I think they have done an incredible job bringing people to the programming world. But yeah, at the end of the day, what we want is to qualify you for the next tasks that you're going to have in life. And learning Python is a great skill to have, because you can do so many things, not only finite elements. Yeah? Good. Other questions? No questions. All clear, yeah?
For the final assignment,
yeah.
do we progress? So can you start working on it and as the lectures go on, you
Yeah.
will get to know more stuff to progress in the assignment, or
Yes.
how do you go through the?
So the question is whether you can progress as the lectures go on in the final project. Yes, you can start with the final project as soon as I post it online. So I will post it on the Brightspace, and as soon as it's there, you can already actually start solving and programming. Of course, to make the first modification, you need to understand a little bit of how you have to compute the force vector. So it will take us some time. So I won't post the final project until I get there. And that will also give me a little bit of time to revise the project, because there are a few modifications I want to make so that it is better than last year. Yeah, but you can, and I would strongly recommend that you work parallel in the final project as you're taking this course, because everything is going to become much more easy. If you wait 1 year, right, and then you have to go online to see the course material again to understand what you need to do for the final project, chances are you're not going to finish this project, right? So, yeah. Any other questions? Yeah?
Is it just the one final project that everybody gets, or is there a different flavor for each person?
Yeah, so the question is whether there is only one project for everybody or everybody gets a different flavor, right? So there is only one project for everybody. In previous years, I was open to suggestions by students, but that didn't go well either. So, besides, now I have someone who is helping me with the gradient, so making everything uniform is better. Yeah? Questions? Yeah?
Are you going to code everything from scratch, or are you going to modify some things in the code?
You were not here? Yes, we're giving you a full working code in Python. Now you have to modify it heavily, right? To make everything work. Yeah.
If this is a prerequisite for enriched.
Yes, it is a prerequisite. This course is a prerequisite.
So do you need to finish the assignment before that course starts?
No.
Okay.
You don't need to finish the project in order to get enriched finite elements, because there is sometimes no time for that, right? So enriched FEM happens in Q4, and basically a few days after this course ends, right? So we don't have much time. So I don't have that restriction. Otherwise, yeah, no one would take my enriched FEM course. And well, as I said, I normally get around 50 to 60 registered students, and then I get around 20 final projects for this course. Well, the enriched FEM, you can imagine that it's way less than that, right? So the guys who really like finite elements get to the next level. Yeah. More questions?
Shall we need to draw the moving picture in our final report?
You have to what?
Draw the picture, draw the image, just like you showed in the slide.
Draw images? Yes, of course you have to draw images. You have to draw plots. You have to show me contour plots. You have to show me some magic, right? Show me that it's working.
But how to draw the moving image? Just the
Well, I'll teach you. I'll teach you to do lots of things in this course. Questions? Yeah?
I was wondering, is enriched finite elements method already used in the industry to a certain extent, or is it mostly still in the research phase?
Yeah, so are enriched finite elements used in the industry, or this is just research? That's a great question. And the answer is there are some implementations of XFEM available in some commercial packages. I know Abacus has an implementation of XFEM. And that's strange to me, because this type of finite element formulations have been around for the last 30 years, right? But they are not greatly used in the industrial setting. So, yeah, not very useful, definitely. A skill to have, for me, a must. But of course, I'm biased. Yeah, if you take that course, then you're going to learn that you can solve problems far more interestingly by choosing functions that are not only polynomials. That is the whole point of enriched FEM. Okay. Any other questions? Yeah?
If I want to do my thesis in ontology optimization, do you think I I'd better take the enriched and finite elements.
If you want to do your thesis in topology optimization, if you should take enriched FEM. Well, the question is depending whether you're going to do your thesis with me or with someone else, because we actually have a really nice topology optimization development that uses enriched FEM in my group. But if you're going to do the final project with another professor in our group, with Matthias, with Fred, they use a density-based approach for which you don't need enriched FEM.
Also, it depends on the approach.
Depends on the I guess the person with whom you're going to work. Yeah. Other questions? Okay. Well, let's stop here, and we're going to take a small break, and then we're going to come back, and we're actually going to start with the material today.